Hello and welcome to CPE350 Chapter 6, Section 6.2, Lumped Heat Analysis. Lumped heat analysis is a trick that's going to enable us to solve transient problems whenever you've got both conduction and convection, but only if we're in a very convection-limited regime corresponding to a Biot number less than 0.1. So if that's the case, we can sort of lump the conduction and convection resistances into a single heat transfer coefficient. And it looks something like our usual expression where heat flow is this lumped heat transfer coefficient U times the area of heat transfer times the temperature difference between the surrounds, which is the fluid, and the temperature of whatever it is that we're trying to cool, which is just a variable T. And we're going to let this equal mCp dt dt. It has to be a time derivative so that the units of both sides of the equation match. And we've seen the right-hand side before. It's our accumulation term from Chapter 4. So whenever we have a transient heat flow, that term is going to appear. All right, so we have an equation. It is a first-order non-homogeneous equation. We need one boundary condition in order to solve it. And so I'm just going to tell you that at time equal to 0, the temperature of the object that we are cooling or heating is going to be T naught. This is also an initial condition because an initial condition is a subcategory of boundary conditions. All right, so T is the temperature of the material that we're heating or cooling, and it is not the temperature of the heat transfer fluid, which is always isothermal for the problem, and it's at TS, which stands for T surrounds. So to work with this equation, we could actually just solve it directly, but I'm going to non-dimensionalize it to give us a little more practice with that non-dimensionalization, and we're going to be using the parameters theta and tau. Expanding the derivative term using the chain rule, we get this expression for dt dt, which we can plug into the equation, noting that we haven't yet actually chosen what we want theta and tau to be, but we use the form of the equation that we derive to sort of decide what makes sense for those definitions of theta and tau. All right, working with our equation, we can rearrange it, and we get a term Ts minus T times d theta dt, which is going to have to be constants. And with some trial and error and some inspection, we can see that it would be really useful for that term to be equal to theta. And so we want Ts minus T in the numerator of theta. And that naturally means that in the denominator, we should have Ts minus T naught, so that theta exists on the range from 0 to 1. So we'll try that definition of theta. We implicitly differentiate it, and then we solve for d theta dt. And if we plug all of that back into our governing differential equation, we get what looks like an algebraic mess. But in fact, these terms cancel, and it simplifies our governing equation. So now we've gotten rid of the dimensional temperature variable. We still need to get rid of the dimensional time variable. And so we're going to choose a very generic expression here. Tau is just T over T star. We're not even going to try to define T star because it will just cancel out actually. So implicitly differentiating, we solve for dt d tau, and then we plug that into our governing equation. So now at this point, we're going to separate the variables, all the thetas on the left-hand side, all the one tau on the right-hand side. T star, of course, is a constant, so it doesn't matter actually which side it goes on. And then we integrate. And we get that the log of theta is equal to this expression with a constant of integration. We haven't non-dimensionalized our boundary condition, so we could either non-dimensionalize our boundary condition and apply it, but what I've done in the lecture notes is to just redimensionalize this equation and then apply the dimensional boundary condition. Either way will work. So to redimensionalize the non-dimensional equation, I plug in for theta equal to Ts minus T over Ts minus T naught. And then I also plug in for tau, which is just T over T star. And you can see that those T stars cancel out. Now we can apply this boundary condition, which is also an initial condition, which says that at time equal to 0, the temperature is equal to T naught. So we plug that in, we get the natural log of 1, which is 0, another 0, and that means that our constant of integration has to be 0. So our lumped analysis equation simplifies to this expression. If we want, we can rearrange it. It doesn't matter which side the negative goes on. If the negative is on the log, we can flip that over so that it's the numerator and denominator switch. All of these forms are equivalent. They're all useful, and they're all going to apply to situations in which we have convective transient heat loss that's very limited by convection, so a low Biot number, less than 0.1. Thank you, and I'll see you again. Thanks for listening, and I'll see you for the last video.